Good morning, everybody. It's great to be here again. We'd like to introduce our talk, EDR equal erase data remotely, reloaded. My name is Tomer Bar, and I'm the VP of Security Research at SafeBreach. I'm a regular speaker at a lot of conferences, and I'm really grateful to be here today.
Hey everyone, I'm Shmuel Cohen, and I've been working in the cybersecurity industry for about 6 years. I began my career as a developer and later moved on to a cybersecurity research position where I did APT research malware. And today my primary focus is vulnerability research at SafeBreach. Back to you, Tomer.
Thank you, Shmuel. So we will start by introducing our research goal and approach. Then we will detail step by step on how we discover the vulnerability and how we use it with at least 10 different attack vectors. And then we will explain how we bypassed this vulnerability, achieved a second one, and even bypassed the second patch and achieved a third vulnerability and a special bonus that we will save for later. Then we will close the talk with the takeaways, the vendor response, and the GitHub repository before leaving time for you to Q&A. So our goal is to be able to confuse EDR by remotely implanting a malware signature into legit files and making them believe the legit files are actually malicious. For an analogy, Defender usually recognizes Taylor Swift as benign. We will try to implant a small mark, and Defender will think that Taylor Swift is actually evil and do his best to eliminate it. So our teaser to conclude is, what will you say if we can remotely delete your critical files over the internet without authentication required, even if you use different security controls on a Windows or fully patched Linux machine? So in the next hour, we are going to prove that it's definitely possible. We had 3 challenges. The first one is that false positives or false alarms are non-problem, right, for a long time. And security controls, which are installed on hundreds of millions of endpoints, are already probably immune to this false positive problem. Moreover, the false positive we are aiming to achieve are even more rare, since we would like to trigger the byte signature engine, which considered to be the most trusted layer with the lowest false positive rate. And the third challenge is obvious: how can we trigger it from remote? So let's begin. The goal of step 1 is to find a signature that will trigger automatic deletion when appended to our own empty file. We decided to use a black box approach this time instead of a white box, since each security vendor product uses a different proprietary database, and our research goal was to discover vulnerabilities in many products as possible. Black box was the best strategy. We also decided to focus first on Windows Defender, which is the default EDR installed everywhere, right? So we assumed that VirusTotal use Windows Defender's same agent as the agent installed on agents. So we try it, and VirusTotal also provide easy hunting capabilities. For example, you can see this query for all detected malware by Microsoft, and we limit it by 200 byte size binary. We ran the query and got 3,600 results. We decided to minimize the file to a minimal byte signature that will trigger Defender. So let's go over a simple example to understand our technique, which is very simple. As we can see in the example, we started with the XABCY detected signature. We removed the first letter X and wrote the file to disk in order to trigger Defender to scan the file again. we still got a detection, so it means X is not part of the signature. But when we removed the A this time and wrote it to disk, we got no detection. So it's an essential part of the signature, and B and C were essential too, and Y is not essential, so the final minimal signature is ABC. We will use it later. So we decided in that point to learn more about Defender threat level by reading the documentation. We found the MP threat class, which includes an interesting field, severity ID. We found out that there are 4 levels of threat severities: low, moderate, high, and severe, and default actions to take for each threat severity. We assume that the most severe threat level will probably have a more severe default remediation action. And we verified our assumption was correct by reversing Defender. And as you can see on the right, this is the logic of the scanner. And so now our goal is to find a severe level signature that will trigger automatic deletion of our file, because low severity won't trigger this automatic deletion. So we continue our manual search for the right signature, but it took us too much time and failed attempts. We found the signatures that are not required manual remediation steps, or signature that just causing part of the file to be removed and not the entire file. So we understood that we should shift from manual process to an automatic process. We downloaded all the 3600 malwares from our original VT query and developed a first basic tool to automatically extract the minimal signature from each malware. The script was very, very basic, just automating the manual process that I've described. We found out that large part of the sample were actually a variant of the same malware, and eventually we found only 130 unique signatures. But how do we select the best signatures for our need? Since we assumed that there are going to be limitations in the implanting of this signature in legit files, we had to prioritize the different signatures in order to find the best signature in the database with the minimum limitations. We believe that alphanumeric signatures will have less limitations. We also might have length limitation, so we would like to use short signatures as possible. The first signature that you see here, the alphanumeric one, didn't work, since it's a base 64 encoding of ACAR, which Defender only deletes if it's the exact content without extra bytes before or after the signature. So we moved on to the second signature, which is only 15 character length and consists of only 2 types of non-alphanumeric characters, a slash and a curly brackets. Let's try to manually add it to an empty file. And actually it worked. The signature caused the deletion of our own file. It was the first time we managed to find a minimal signature which successfully triggered automatic deletion of our file. But deleting our empty file is not interesting, right? So our next step was quite obvious, verifying that we can manually append the signature to a target legit file. And we tried, and it didn't work. We embedded it into a middle of existing document in the middle, and nothing happened. So we go back to the drawing board and develop another faster minimizer. This time, it calls Defender scan exported function instead of just dropping each instance to disk and have to wait for detection as we did with the first minimizer. This is much, much faster since Defender does not quarantine the files after detection. This tool just reads the target malware from excluded path and replace each byte with just a random letter, Z, and rescan it. If the verdict turned to be 9, then we restore it back to the letter, the Z, and move on. So let's see an example when we run it on Mimikatz. So when we append Mimikatz signature to the middle of legit portable executable files, like application, it works. The problem is that we could not think of any interesting attack vectors on PE file. So if the user already have privileges to write to a PE file, he probably can delete it anyway, right? So we have to focus on non-executable files, non-application, and understand the reason why it failed to detect our signature. So we developed a third tool to understand the non-PE limitation. The tool is also very simple. Try to embed the same signature in incremental offset from the beginning of the file to its end. We found out that in the case of non-PE files, Defender does not scan the entire file. It's actually scan only the first and the last 4,030 bytes, probably for efficiency reasons. So it means that we must append our signature to those sections in the target file, but if we can do that, we will be able to delete non-PE files automatically. So until this point, we were focused on learning how to locally trigger automatic deletion. Now we should plan how to achieve remote attack vectors. So we needed a way to somehow make a privileged service to write our data to a remote file. So we started thinking, and the first idea that came into our mind were logs. If we will be able to send an HTTP request with our signature to a web server, and this web server will log our request, we will be able to trigger the remote defender, and which is installed on the web server, to delete the log file. And then we start thinking which HTTP field we should use. And we look at IIS logs, for example, and we saw the user agent field, which is a long free text field, which is written entirely to the log file daily. And the best was that all client requests actually are written to the same file. So if you serve to a server and I serve to a server, it's like ends up in the same place in the same log file. So it should be the perfect place to include our signature. So now let's explore the first attack vector. We'll have plenty, so stay tuned. It will be the remote deletion of IIS web server logs. Shmuel will introduce it.
Thank you, Tomer. Okay, so now we will have a series of demos and attack vectors that we found. It's going to be very, very interesting, so stay focused. So first demo, remote deletion of IIS web server logs. So at first, we have on the right side a virtual machine with an IIS web server logs installed. I'm surfing into this IIS web server, and it's just to show you that every time that I surf into the web server, we will see it logged into the log files. So on the victim machine, I'm just showing you that logs has been recorded. And now we will use a very simple tool that just sends a HTTP request with a malicious user agent to the IIS web server on the victim remote machine. And let's see what will happen. So after sending the user agent request, we can see that immediately Defender detects this log file as malicious, and this log file will be deleted with all of its content. We also verified that this method is working on Windows servers as well. Even if no one tries to open the log file, after a few minutes, Defender will automatically detect that as infected log file and will be deleted. As you saw in the demo and you see in this picture, Defender detects the IIS log as an RTF exploit. It's because of the RTF exploit signature that we've used, and it will be deleted after a reboot. Well, IIS is a good example for Windows servers, but most web servers are installed on Linux. And in Linux, there is no EDR installed by default. So we aim to trigger other EDR solutions that are likely to be installed on large number of Linux web server machines. As you can see, according to Gartner Magic Quadrant, these are the leading EDR products on the market. we aim at them since they are likely to be installed on enterprises' servers. As of now, we confirm the effectiveness of our technique, and we now have the ability to automatically reduce the size of signature in a way that would trigger automatic deletion. With this knowledge, the next step was to create a database of what we call as evil signature, and for various leading EDR vendors. This database will allow us to perform single signature queries capable of triggering most, if not all, of the EDR solutions. This method is beneficial for remote attacks when we don't know which EDR is installed on the remote machine. As we explore different EDR solutions, we notice variations in their behavior, probably because of how they implemented their EDR solutions. However, our investigation led us to discover that Kaspersky EDR demonstrated the exact behavior that we were searching for. Therefore, in the upcoming Linux examples, we focus on targeting Linux servers with Kaspersky EDR installed on them. Another side goal that we had is to find a signature that will trigger most of vulnerable EDRs. This will be perfect in a case when we don't know which EDR is installed on the target machine, so we can use this signature and it will trigger it. Let's see what happens now on Linux using an Nginx web server and Kaspersky installed as EDR. So in this image, you can observe an Nginx web server installed on Ubuntu machine. Highlighted within the red box, you can see the malicious signature that I'm going to send to the victim. Using a basic Python script, I send this malicious payload disguised as a user agent to the Nginx web server, and at the moment that I've executed this command, Kaspersky instantly detected this log as malicious and deleted it. The same method effective on Apache web server as well. In summary, by using a very short signature, we allegedly will be able to remotely delete up to 35% of web server logs in the world. This is pretty crazy. We've demonstrated with Kaspersky on Linux, but it could be potentially extended to other security vendors as well. In the following slide, we'll showcase a brief of examples for various attack vectors that we identified. The first one will be an FTP server. Not only web server logs are at risk. FileZilla FTP server will be at risk too. This time by using a signature minimized from the invoke Mimikatz PowerShell malware. We used it as a username for the FTP login, as you can see. This malicious username will be written to the FTP server logs, which will cause Defender to delete it. Another cool attack vector is an email attack scenario using Mozilla Thunderbird. The attacker sends an email to the victim with a subject including the malicious signature. Then, as designed, Mozilla Thunderbird stored the entire inbox in a single file. A single textual file contains our signature. The local inbox will be removed by the EDR. Then Thunderbird will download it once again. Then it will be removed once again in a non-stop loop of downloading and removing the same database file. Another cool vector is by executing a corrupted MSI file. The subject field in the MSI properties will include our evil signature. This will cause a log record that contains the evil signature to be appended to the application Windows event log file. This will trigger Defender to delete this file. This is not the end. What about achieving a deletion of Windows event logs but remotely? Is it possible? The answer is yes. By attempting to perform a remote login to the machine via SMB, using a malicious username, we can remotely insert malicious records into the security event log file. If we repeat this process enough time, the record will end up at the end of the log file, resulting their deletion. Let's see a demo of this deletion of remotely delete security event logs. So the same, I'm getting the IP address of the victim machine. Then another simple Python script. I just send a lot of SMB login requests to the machine with a malicious username, of course. It takes some time, so I'll short up the video a little bit. And we can see that after the script has finished, I'm just to make things quicker, I'm manually scanning the event log directory, and we can see that the security event log file is now considered as a malicious file, and it will be deleted with all the information it contains. Self-cannibalism. How do we make Defender deletes its own log, its own detection logs? It's done with an unprivileged user, when even an administrator doesn't have the permissions to even read the content of the file. Let's see how we did it. So at first, I'm creating a folder, and I'm just name it as a malicious signature. So this by itself will trigger Defender, as you can see. But this trigger of Defender will log all the triggers details inside Defender logs. So if we scan Defender logs folder, it will contain the malicious event that just happened. And we can see, just 1 second. OK, now we can see that now all of Defender event logs and security logs are now considered as malicious, and he will delete its own logs. So this one was pretty funny. OK, so now we understand how we can remotely delete logs, but we can achieve even more. Let me ask you a question. What happens to logs in enterprises? Well, as all rivers flow to the sea, all logs flow to a SIEM database. For example, Splunk, which is a central point to monitor, search, and analyze logs. Let's see how we may trigger a domino effect against Splunk. We verified it by manually adding a log file with a name that includes the evil signature. Splunk will write the name of the file into its database, and this will cause Defender to delete Splunk database. The same goal can achieve automatically as a result of the domino effect when we infected Windows event logs. So the event logs will be collected automatically by Splunk, and it will be added to the Splunk DB, which again will cause Defender to delete it. And logs are definitely not the only thing that we can attack. Let's see 2 virtual machines attack vectors done under VMware. So we started by taking a look at the VMX file of the guest machine, which is the configuration file of the VM. This file is mandatory for the machine to boot up. Without it, the machine simply cannot boot up. We wanted to check if the guest machine can write data to this file in order to implement a malicious string to it. This file is presented on the host machine. So we need a way to write data to this file from the guest machine. We searched for communication originated from the guest machine to the host, and after digging a little bit, we found that VMware tools provide a tool called RPC tool that allows you to communicate with the host machine. One of the things that you can do with RPC tools is set global variables, that some of them are like the guest info.detail.data variable, as you can see in the picture. This variable is kept in the VMX file on the host machine. So if we set this file, this variable in the guest machine, it will cause this data to be written on the VMX file on the host machine. So if we send our evil signature, for example, this might be achieve a deletion of the VMX file on the host machine. And as you can see, at the moment I pressed enter and executed this command, we got an error message that the VMX file is unavailable. This means that the guest machine cannot boot up again. So from the guest machine, we got a total DOS attack, and this machine cannot boot up again. But wait, there's even more. This attack is nice, but it targets only the configuration file. What about targeting the entire virtual machine data file itself? Is it possible? The answer is yes. Let's see how we did it. So we did it by creating numerous amount of malicious files within the guest machine. In this example, we created about 100K files on the guest machine, and this will cause all of those files to be written on the VMDK files on the host machine. The VMDK files are all the files that contains all the data of the entire virtual machine. So after running my script that creates a lot of files, we can see that when I'm rebooting the guest machine, it cannot boot up again. All the files are now considered as malicious, and all the data of this virtual machine will be lost. Okay, so the crown jewels of most organizations aren't stored in files, rather they're stored in databases. While we primarily focus on deleting logs and configuration files, the question arises, can we potentially delete an entire production database over the internet without any authentication? So typically users don't possess the privileges to directly insert queries into a remote database, right? However, it's common for websites to rely on a backend database for operations. For example, consider a scenario when a website features a new user registration form. By submitting our malicious data through this form to the database, such as registering a new user with malicious username, we have the ability to remotely prompt a defender to delete the entire database without requiring any form of any authentication. So let's see a demonstration of this attack. So on the left, we have MySQL installed on a Linux machine with Kaspersky EDR installed. On the right, we have web access to the database. At first, I'm just inserting an example to show you that the database is really working. And the second one will be a malicious signature. We insert it into the database, as you can see. And a few seconds after, we can see that Kaspersky found this database as malicious. And we can see that this database is no longer working. The database service has crashed completely. And even if we try to restore the database files, Kaspersky immediately detects them again as malicious, as you can see, and keeps deleting them over and over again. And actually, even if we try to shut down Kaspersky and restore those files, the database simply cannot start again. So it will totally corrupt your entire database. The attack is effective as well on Windows with the Defender or other vulnerable EDR solutions. Upon implementing the mimicked signature into MariaDB database, the database file is flagged as malicious. This not only risks the potential data loss, but can also cause database services to become inaccessible. Even attempts to restore it from quarantine or external backup fail to restore the functionality, as I explained earlier. We've tested our attack against some most of popular databases around the world. In the same way, we were able to remotely delete PostgreSQL, SQLite, and MongoDB on both Linux and Windows platform with vulnerable EDR installed. Considering the widespread use of those 4 different databases, the potential of impact on major websites is significant. Up until now, we've explored various remote attack vectors targeting servers and services. Now we'll shift gears and demonstrate the reverse scenario, when a web server can launch attacks against a client browser. When an attacker sends a link to the victim, once clicked, the victim browser sends an HTTP request to the server. The malicious web server then responds with the signature, perhaps hidden within a cookie. As a result, the victim browser logs the response into its local database, which then triggers Defender to delete it. In this example of remote deletion, we remotely delete from a malicious web server the entire Chrome history and web data database. We believe that the 10 attack vectors that we've discovered are just the tip of the iceberg, and regarding cloud attack, literally the sky's the limit. With Defender embedded in numerous critical points across all over major cloud vendors, the potential damage is significant. Let's now see the vendor responses. We reported to the relevant vendors at the beginning of 2023. Microsoft issued a fix to this vulnerability on April 2023 with the CVID that you can see on the screen. Kaspersky did not release a patch, but they plan to mitigate these attacks as well as part of their change in their engine's designs. But this is not the end of our story. Let's get back to Tomer.
Second. Do you hear me? Okay. Okay, so cool until right now, right? So, but this is not the end of the story. Immediately after the patch release on April last year, we started to check the original attack vectors and found out that not all of them were fixed. But we delayed the in-depth analysis to August. And this is one example that we found, an unprivileged deletion of Defender detection logs, which were still possible on fully patched machines by the time of the check, and actually it's still possible nowadays. So after checking out of the attack vectors we originally reported on January last year, we were able to see that almost half of the attack vectors are still valid. On the left, you can see a list of attack vectors that were fixed, and on the right, a list of attack vectors that were not fixed by the original patch. So we started focusing on MySQL database, which is one of the most prevalent databases in the world. And MySQL has a default storage engine, which is called InnoDB. The file size is dynamic and enlarged once insertion of new data is reaching the size limit, which is in default 3 megabytes, and causing the vulnerability not to be triggered, since if you remember, we need to embed our data into the end of the file, because Defender does not scan the entire file. So our signature is never written to the file location scanned by Defender in this example. But InnoDB was not always the default storage engine. MyAwesome was the default storage engine until MySQL version 5.5.5, and MyAwesome file size is not dynamic, and when inserting a new data, it will be appended to the end of the file. This might be vulnerable, so we gave it a shot and tried our signature on MySQL using MyAwesome storage. So by now you know the drill. We'll take the IP address, and we are running MySQL. We'll show that it's after the patch, so it's fast, but you can see the date. It is after the patch release at April. It's the end of July. And we'll start the attack. And automatically Defender triggers. Let's see on what. So it's the entire database file, and the service is not available anymore, and the attack is finished. So Defender detects the MYD file as an MS Office vulnerability and deleted the database file, as you saw, and caused denial of service and also data loss. But MySQL 5 is very old, right? But there were very common installers like WAMP, which stands for Windows, Apache, MySQL, and PHP suite, which use MyAwesome actually as the default storage engine and made this attack still relevant today because it's a very common installer. And this was our first bypass of the patch. But we wanted to be able to bypass MySQL deletion defense in other databases, even if they are using the latest default storage engine. So when looking at the table, it's quite easy to see that all the files on the left and marked with green color are stored in binary format, while all the files on the right are stored in textual format. So it seems that the patch changed Defender behavior when scanning a file. It triggers a detection when a textual file includes a textual script based on malicious signature, but it ignores the signature when the file is in a binary format. What will happen if we'll use binary signature on binary formatted database instead the textual signature that we used before? We tried all the signature we collected from our signature DB using a simple script, and we found out a signature named Levinian K, which triggered Defender to delete the database in a fully patched machine. Here is a demo of the bypass. So again, you can see that it's after the patch. You can see the date, version. We'll do the attack again, and this time it's an InnoDB storage engine, which is the default storage engine. So again, running the MySQL, running the attack, waiting a few seconds, and automatically Defender should trigger. And yeah, it's happened. And this time it's not an MYD file. You can see that it's a redo, which will cause the database to be ruined. Even if you save a backup of the database externally and try to restore it from the backup just after a minute, it won't work. The database is totally ruined. Even a restart, service restart, OS restart won't work. Trust me, you cannot get the data back again. So Microsoft released a second patch, CV 2023-36010, on December last year. And guess what was our next move? So we analyzed the patch once again. Let's see what we managed to achieve. So we found out that the patch did not fix at all remote deletion of MySQL InnoDB databases. It's still vulnerable. You can see that it's a fully updated Defender on December, including the patch and the second patch, and the signature was inserted into the DB, which triggered Defender. Let's see if the patch had logic to fix the MySQL myAwesome remote deletion. So we checked it out and found that indeed it was focused on this myAwesome format. And they did it by adding a whitelist algorithm based on the myAwesome file format. So Defender checks if the scan file starts with FD, byte, and if the file size is aligned to 256 bytes. If both conditions are met, it won't be triggered. You understand that it's a database, and it should not trigger a detection, even if it detects a malicious signature inside of it. So our goal now is to bypass the whitelist to trigger the deletion of this database file. So of course, we don't have control over the first byte of the database. So we focused on the size of a record. The default length value of a textual field is 256 bytes. But it's not true for any database that use non-default textual fields length. And according to MySQL manual, a text field can reach a length up to 65,000 bytes. So what will happen if the victim's DB use a non-default textual fields? As we can see, we were able to insert our Levinian K signature into a field larger than 256 bytes in the MySQL myAwesome database and bypass the whitelisting logic. We were able to bypass almost all attack vectors fixed by the two different patches after a year from the original report. So you can see only 3 attack vectors we were not able to bypass. But as I promised a special surprise. So beside bypassing the second patch, it also introduced a Windows Defender generic detection bypass. So if you remember the whitelisting logic added by the second patch, what if we can turn a non-malicious IOC to be whitelisted by Defender due to a security patch? That's funny, right? So we know that PE files must start with the MZ magic to work. So we didn't focus on that. We focused on script instead. And we tried to add the FD byte to the beginning of scripts. But it's, of course, not a legit script command. And so we tried to bypass this limitation. And we found out that PowerShells support a special command. It's called error action preference. And you can set it to ignore. So even if you have a wrong command, the FD command, it will just skip it and execute the entire script after it. So we bypass this preference. And to align the file to 256 bytes, it's very easy because you can add a comment and just calculate the file size, add it to a line to 256, and then you have a full bypass. So we just developed a 17-line script. We call it PowerFD. It's PowerFD because FUD is like the known for fully undetectable, and PowerShell, of course. And actually, it's 17 bytes of code. You take any script you want. We just took out Mimikatz, which like dump LSAS memory, which is very famous from PowerShell Mafia, I think. And we just took the file, run this script over it, and now Defender does not detect the file anymore. So let's continue to the vendor response again. So Microsoft thanks us and confirmed all the bypasses, but decided not to fix the last one and not to release the third CVE. Instead, they add improvement and configuration to reduce the risk of false positive and data loss. Regarding the Defender bypass, Microsoft confirmed the generic bypass, but again decided not to fix it since the attacker must also achieve initial access to the device. So there are attack vectors that are still relevant today. And if you would like to test it, this is, of course, the entire timeline, which was like more than a year. And if you would like to test it, this is our GitHub repository, where you can find our EDRacer tool, which supports all the attack vectors that we discovered, and even allow you to expand them to new attack vectors very easily. So I encourage you to try it and see if you can like find new vulnerabilities. Let us know if you find some. And I will wait a few seconds for you to take a picture of the QR code if you want. And let's move on to the takeaways. So I think that it's very obvious that remote deletion vulnerabilities are very difficult to fix, especially when the security control relies on the byte signature detection. And the second takeaway is that security patches might be incomplete, as we saw. Patching should not be treated as a magic bullet, and other security layers should protect against single point of failure situation. And lastly, security patches fixing vulnerabilities in security controls might introduce bypasses and unexpected behavior.
Thank you, everyone.